Hi everyone, now I'm presenting the video about a natural log transformation and power model using Minitab, presented by me, Mateo Banchon, and Jeffrey Bennet. So we are giving you an example about a correlation between the length and the pendulum in centimeters and the time it takes to make a period in seconds. And there is a Minitab after the power model transformation with the constants and the slope. And also there's the graph before the transformation and after the transformation. And there are three simple questions. A, in basis of the graph, explain why it will be reasonable to use a power model to describe the relationship. B, write the equation of the LSRL and define the variables correctly. C, with the equation of part B and B, try to predict the period of the pendulum of 50 centimeters. But why we need to transform the graph? Why we need to make it more linear? To explain that, now Jeffrey's gonna make you a visual representation of how it will work.
Hello, my name is Jeffrey Bennet, and today we'll be using sodas to describe how logarithms can transform an equation. So basically, a logarithm changes the correlation to be stronger if the correlation isn't strong enough. So similarly, in a Coke bottle, shaking it can reduce the carbonation within it. So I'm going to do that now. You gotta shake it real good to get the carbonation out to transform it into a non-carbonated beverage. Okay, so I just got that all over myself. But as you can see, there's still some carbonation within the soda, such as in a logarithm model, there'll still be some type of lack of correlation within it. However, that is when we also do a power model. A power model is where you log both sides of it to get the ultimate, to show a stronger correlation. So now we're going to not only just shake it, we're going to put a Mento in it. We're going to do two things to it to transform the soda to non-carbonated and get the ultimate transformation of it. So here's a Mento. I'm gonna have to back up for this. See? And that is how you get the ultimate transformation, as it gets all over my table. However, there's still more complexities. Look, it's still going. There's still more complexity to logarithm, since there is natural log and normal log, which will be described in the next segment of this video. Thank you.
And that's why it's reasonable to use a power model, because the graph it begins with a very curve, and after doing the first transformation it's still curved. That's why you need to do a double transformation, a power model, so it will be approximately linear. Then we also have the natural log that's happen when the exponent base is the e value. So then there's an example of how it looks like the log base will be ln. It's just the same thing. Then we have the transformation. How will it be? So instead of log, you will put ln. That's the. And in part B, write the equation of the LSRS with the modifications and the variables. When transformed the first time, the logarithm will you put it in the y estimate. So instead of just y, it will be log y. And then for the second transformation, the power model, you also put the logarithm in the x variable. Then remember, the a is the constant and b usually is the x or the long length or the slope. And it's the Minitab when it's the data, and then just substitute that data from the Minitab to the equation, and then you get the equation. Last but not least, part C, with the equation in part B, try to predict the time it takes to a pendulum of 50 centimeters to make a period. So first we put the equation we only got in part B, and then substitute the value of x by the value they gave us, that's 50 centimeters, and then start solving. That will give you Log of y estimate is equal to 0.141736. Then we do the inverse of logarithm. Because it's normal logarithm, that's by base 10, so it should be 10 to the exponent of 0.1417. And then that will give you a y estimate of 1.3859 seconds. Thank you for watching.